Hey, it's Mr. Sanford again with your limiting and excess reactants notes part 2. So we just saw how we could use particle models or particle diagrams to figure out limiting and excess reactants based on how many leftovers we had and which one did or didn't have leftovers. But what if you don't have a particle diagram? What if you don't have a particle model? What can you do? We're going to learn about a new model called a before-after change table. We're going to abbreviate that BCA table. So B for before, A for after, C for change. So there are going to be 3 sections of this table we fill out based on the given information. So the before section is going to be the number of moles given to us. So everything has to be converted to moles in order to use this table. So if you're not given moles of something, you have to do that conversion first, and then we can plug it into the table. So again, everything in the table is going to be in moles. There will be a change line on our table. So we will take the moles of reactant that get lost or used up, and the moles of the products that are gained or made during the reaction according to the mole ratio. So we're going to have to fill that information in ourselves. And then the after line on the BCA table is where we're going to see the moles of reactant that are left over, if there are any, and the moles of the products that got produced. So let's go ahead and do one together. So here's an example. We want to determine the number of moles of water that can be created when 6 moles of hydrogen gas are reacted with 2 moles of oxygen gas, according to this balanced chemical equation below. So the before line is where we're going to use the information that they gave us in the problem. So it tells us right here that we're going to start off with 6 moles of hydrogen. So before the reaction actually happens, we have 6 moles of hydrogen gas. So we put that right under H2. We also are told that we have 2 moles of oxygen gas. So we plug that in under O2. And before a reaction happens, what we've got to realize is that there aren't going to be any products. So before, the products are always going to be 0 moles. Now we have to fill in the change line for our BCA table. And so this is the part that gets a little tricky, where we have to use the mole ratio of the things in the equation to figure out what the change is going to be. So let's first take a look at this mole ratio. 2 moles of hydrogen to 1 mole of oxygen. So we always have double the hydrogen than the oxygen we do, right? That's what that mole ratio is telling us. So we need to figure out what we're going to be able to use and what we're not going to be able to use. So see how we're starting off with 2 moles of oxygen? And this is telling us for every 1 mole of oxygen, we double it to get the hydrogens, right? So if we double 2, that means we're going to have 4 moles of hydrogen here. So again, if we start off with 2 moles of oxygen, the mole ratio tells us to double it. So then we're going to have 4 moles of hydrogen. Right? And so changes, reactants always go away. So if we're using all 2 moles of the oxygen, we're going to do minus 2 moles. The mole ratio tells us that that's going to react with 4 moles of hydrogen. So we subtract 4 there. Now, another way you could have seen this is, or looked at this, is we could have gone the other way. We could have looked at, for every 2 moles of hydrogen we use half the amount of oxygen. So if we were to use 6 total moles of hydrogen, half of that would be 3. Did we have 3 moles to use, though? No, it tells us we only start with 2. So if we choose to start with 6 as our subtraction, we're going to find out pretty quickly that if we do 2 minus half of those 6, which would be a 3 here, that's not going to work. We're going to be left with a negative number of moles, and that just can't happen. So by checking both ways, you can determine that you've got it set up the right way. All right? And then let's take a look at how we're going to figure out what to put for the change for the product. Now, products are always added because you're creating things, so we're going to add those numbers. But look at the ratio between hydrogen and water, 2 and 2. So those are identical, right? So our moles here for hydrogen on the change line and water on the change line should be identical, except for the math function that we're doing. So this one's going to be subtracted, and this one's going to be added, right? Because in reactions, reactants go away, and they form new things, and so we get products. So we subtract the reactants and add the products. Now we've got everything filled out for the change line. We just need the after line. And this is pretty straightforward. You just do the math. So 2 minus 2 is going to leave us with 0 moles of oxygen. 6 minus 4 is going to leave us with 2 moles of hydrogen. And 0 plus 4 is going to leave us with 4 moles of hydrogen. Now that we have this after line, this is what happens after the reaction takes place. So we can take a look and we can figure out how much product we got, 4 moles. So we can do a little analysis here. What was the limiting reactant? Which one ran out first? That would be the one that goes to 0. Oxygen was our limiting reactant. And then which one was in excess? The one with leftovers. Hydrogen had leftovers. So, and we can even determine how many leftovers there are, or how many moles of excess there are. 2 moles. The BCA table will tell us that. Let's do a second example together. So let's model how we're going to do this. So we've got to figure out the number of moles of ammonia when that are created when we have 6 moles of hydrogen gas. They're going to react with 3 moles of nitrogen gas, and we've got our balanced equation here. So again, the before line, we're always going to fill in the information that they give us and what we can know logically. So they tell us 6 moles of hydrogen gas, so we're going to put that in. They also tell us 3 moles of nitrogen gas, so we're going to put that in. And we know that before this reaction happens, there's no ammonia, so it's 0 moles. Right? Now let's figure out the change line. This is where we look at our mole ratio. So let's look at this one. 3 moles of hydrogen and 1 mole of nitrogen. So every time we use 1 mole of nitrogen, we have to triple it for the hydrogens. Or look at it backwards. Every 3 moles of hydrogens, we have to divide it by 3 to get the moles of nitrogen. So let's look for a moment. If we choose nitrogen as our starting off point, and we're going to subtract 3 moles here, right? We have to triple that to do the number of hydrogens. Well, 3 tripled is 9, so we would have 6 minus 9 moles, which would give us a negative number, and that's not going to work. So we're going to start with hydrogen. Right? So we're going to subtract 6 moles there. And because we're going to divide it by 3, we're going to take a third of that amount based on this ratio. A third of 6 is 2. So for every 3 hydrogens, we're only going to need 1 nitrogen. If we're using 6 hydrogens, that means we only need to take away 2 moles of nitrogen, right? And now we've got to figure out the change line for ammonia. So we need to look at a different ratio because none of ours are the same up here. So let's look at this ratio, 2 moles of NH3 for every 1 mole of nitrogen. We already figured out that we're going to subtract 2 moles of nitrogen and take a look. For every 1 mole of nitrogen, sorry about that getting in the way, we're going to have to double what we have to get the moles of ammonia. So if we're taking 2 away here, we double that, we're going to add 4 moles of ammonia. So now we do the subtraction. 6 minus 6 is going to leave us with 0 moles of hydrogen. 3 minus 2 is going to leave us with 1 mole extra of nitrogen. And then 0 plus 4 is going to leave us with 4 moles of ammonia. And we can do a little analysis here. What was our limiting reactant? The one with 0 moles, right? The one that ran out first. That would be hydrogen. What was our excess reactant? The one that had leftovers. The reactant with leftovers. Nitrogen. How many moles left over were there? 1 mole. And then how much product do we get? In this reaction, if we had these starting products, we would get 4 moles of product.